Hello everyone, my name is Adil Raza, and in this video we are going to learn about electric field lines, Gauss law, and lastly few instances where Gauss law is applied. Okay, let's begin. These are the topics covered in this video. Pause the video if you wish to go through it. Electric field. Electric field due to a source charge capital Q at some point P is the force that a unit positive charge small q would experience if placed at that point. What do I mean by this? Imagine that there is a source charge capital Q and you have to calculate electric field at point P. You will place a positive test charge at point P and you will calculate the force experienced by this small positive charge using Coulomb's law. And then you will, if you wish to find out the electric field at point P, you will simply divide this force by the amount of test charge. Okay. Mathematically, electric field is defined as electric field is equals to limit small q approaches to 0 f by small q. Why this limit? Because we want this small positive test charge to be as small as possible. In that case, it will not be able to affect the electric field due to the source charge. Fine. So you will finally get the expression for the electric field as kq by r square r cap. Fine. And if you wish to calculate net electric field due to a system containing n discrete charges, then you will use this formula. This formula suggests that net electric field is the vectorial summation of individual electric fields due to individual charges. We will have this expression. This expression comes from the principle of superposition. And if the distribution is continuous, the distribution or charge distribution is continuous, then we will use this expression in the integral form. Fine. Okay. So far what we have learned that electric field is a physical vector quantity and depends only on the source charge and the distance from it, because as you can see the small q cancels out. It doesn't depend upon the small test charge, it depends only on the source charge. Fine. Let's move to the next slide. Electric field lines. Electric field lines are curves to graphically represent electric field on paper. Unlike electric field, which is a physical vector quantity which we have discussed earlier, electric field line is not physical quantity. It is just a convenient way to visualize electric field. What do I mean by this? Imagine that you are provided with electric field lines in a region and you wish to find out the electric field from the given curves. How will you do that? First, we will talk about the magnitude. Take 2 points in that region, point A and point B, and then draw an equal amount of cross-sectional area around point A and around point B. Then you count the number of electric field lines crossing each area. As you can see, number of electric field lines crossing around point A is 4 unit and around point B is 2 unit. That means if you say that the magnitude of electric field at point A is E, then you can safely say that the magnitude of electric field at point B will be half of it. That is, the magnitude of electric field is proportional to the density of electric field lines. And that's how we get the magnitude. What about the direction? Imagine that you have to find out the direction of electric field at certain point P. You simply draw the tangent on that curve and the tangent will give you the direction. Fine. I have drawn electric field lines in 3 instances. First, in case of a positive charge, second in case of a negative charge, and third in case of a pair of positive and negative charge. Fine. Let's move to discuss properties of these electric field lines. Properties of electrostatic field lines, that is, electric field lines due to charges at rest. Electric field lines start from positive charges and end at negative charges. Or you may say that electric field lines emerge from a region containing the positive charge and electric field lines sink into a region containing the negative charge. Or you may say that the positive charge behaves like a source of electric field lines and negative charge behaves like a sink for electric field lines. Fine. And what about a region containing no charge, a charge-free region? Electric field lines will be continuous in such region. Why? Because electric field line will neither vanish, will neither emerge from an empty space, like in this case. In this case, electric field lines are emerging from thin air, nor electric field lines will vanish into thin air. Therefore, this cannot be the case. Electric field lines cannot be discontinuous. Electric field lines has to be continuous in a charge-free region. Fine. Let's move to the next two properties of electrostatic field lines. Electric field lines never cross each other, because if they did, at the point of an intersection, we will be able to draw two tangents, and electric field at that point will have two directions, which is physically impossible. As shown in this diagram, electric field lines are crossing at certain points, and at any such point, at point P, we will be able to draw two tangents. Therefore, we will have two directions for the electric field at point P, which is physically impossible. Therefore, this can never be the case. And electrostatic field lines do not form closed loops. Why? Because if electrostatic field lines will be able to form closed loops, then electrostatic field lines will not be considered conservative fields. You will learn about that later. And we will not be able to define electrostatic potential for the electrostatic field. That's why this cannot be the case. Fine. Electric flux, which is represented by this letter phi. Electric flux is a measure of number of electric field lines crossing a given area, which is placed normal to the field. It is a scalar quantity which is proportional to the number of field lines crossing a given cross-sectional area. And if the given cross-sectional area is not normal to the field, we take the component of area which is normal to the field. That is, if you have to calculate electric flux, you will take magnitude of electric field times component of area which is normal to the field. That's how we will get E times A cos theta, where A cos theta is the component of area which is normal to the field. That's how you will get electric flux is equals to area dot product of area vector and electric field. Fine. For example, in this given case where uniform electric field is crossing the shaded region and you have to calculate the electric flux, how will you do that? You will multiply the magnitude of electric field with the component of cross-sectional area, a given area. Suppose the given cross-sectional area is making an angle theta with the field. Therefore, the component will have its value A cos theta. Therefore, electric flux will come out to be E dot A. Fine. And if you have varying electric field, then you will calculate electric flux by this formula, that is electric flux is integration of E vector dot dA vector. Fine. One last point, keep in mind the sign convention. Flux leaving a closed surface area, that is, imagine that this is a cube, this is a closed surface area, and the flux due to the electric field lines crossing this and leaving this surface area phi 1 will be taken as positive, and electric flux due to electric field lines entering the area phi 2 will be taken as negative. Therefore, phi net will be equal to phi 1 minus phi 2. Fine. Let's move to the next slide. Finally, Gauss law. So far, we have learned how to calculate electric field and electric flux. Now we will see how this electric flux leaving a region relates to the electric charge in that region. Imagine three closed surfaces as shown in the figure, and in each case there are some electric field lines entering and leaving, but you cannot see what is holding within each surface. You cannot see what is inside of them. Can you tell which of these surfaces contain positive charge, which of them contain negative charge, and which of them contain no charge, just by looking at the number of electric field lines entering and leaving? Let's see. In case 1, as you can see, number of electric field lines entering or leaving are equal. And we have already seen that electric field lines are continuous curves in a charge-free space. And in this case, whatever the field lines are entering are also leaving. Therefore, you can imagine that the region within the surface in case 1 is not contributing any electric field line. From this, you can say that the region must be empty. That is, net charge inside this surface must be 0. Fine. Let's discuss the second case. In case 2, number of electric field lines leaving the surface is greater than the number of electric field lines entering the surface. That is, the region must contain some positive charge, some positive electric charge from which those extra field lines are emerging out of this surface. Therefore, net charge inside the surface must be positive. And what about the third case? We can say that number of electric field lines entering the surface is greater than the number of electric field lines leaving the surface. Therefore, the region must contain negative charge into which those extra field lines are vanishing into. Fine. So what we have learned, just by looking at the number of electric field lines, we can comment about whether that surface contains positive charge, negative charge, or no charge. This is what Gauss law is. Gauss law tells us the relationship between electric flux and the charge within that surface. And this is the expression of the Gauss law. That is, electric flux integration, electric flux over a closed surface it will be equal to QEN divided by epsilon naught. QEN, what is QEN? It is the charge within that surface, and this is epsilon naught, permeability of the free space. Fine. And such surfaces are considered Gaussian surface. And this Gaussian surface does need not to be physical, it can be imaginary as well. Fine, let's move to the next slide. You might have noticed that we did not derive the expression for the Gauss law in the previous slide because it involves the concept of solid angle and it is beyond the scope of your syllabus anyway. That's why I am skipping the proof of Gauss law, but I will verify the Gauss law, the expression for the Gauss law in case of a point charge. How will I do that? I will take a Gaussian surface, a spherical Gaussian surface of radius r, centered at the point where the where the point charge capital Q is placed. I will take a small area dA, this, and I will find out the flux crossing this area. We already know that the expression of the electric field for a point charge is kq by r square r cap. We have already seen in the previous slide. Therefore, d phi will come out to be E dot dA is equals to kq by r square r cap dot dA r cap. R cap, the dot product of r cap and r cap will become 1. We will be left with kq by r square dA. Therefore, net flux will be equal to integration of d phi over a closed surface, the Gaussian closed surface, and its value will be equal to kq by r square integration of dA. And value of k will be 1 upon 4 pi epsilon naught q by r square. And what will be the integration of this? This will be the area of the sphere, which will be 4 pi r square. As you can see, 4 pi will cancel out, r square will cancel out, and we will be left with electric flux is equals to q upon epsilon naught, which is the expression for the Gauss law. Therefore, we have verified the expression of the Gauss law in case of a point charge. Let's move to the next slide. You might be wondering that what is the use of Gauss law, because Coulomb's law also gives the expression for the electric field. What is the use of Gauss law? Calculating electric field using Coulomb's law will become cumbersome if the system involves multiple charges. That's why in such cases Gauss law becomes useful. Gauss law is useful to calculate electric field when the charge distribution is uniform. For example, we will calculate electric field due to a uniformly charged infinitely long straight wire and the line charge density lambda, which is charge per unit length, is given. Okay, how will I do that? I will take a cylindrical Gaussian surface because the symmetry is cylindrical and the electric field due to this infinitely long straight wire will be radially outward. Therefore, I will take this to be the Gaussian surface and I will calculate the electric flux leaving this Gaussian surface. As you can see, electric field lines are radially outward, therefore there will be no electric flux crossing the flat surfaces. Therefore, total flux will be equal to E times curved surface area of the cylinder. Fine, and its value will be equal to E times 2 pi RL. The curved surface area of a cylinder is equals to 2 pi RL. Fine, and by Gauss law we know that flux is equals to Q enclosed divided by epsilon naught. What is Q enclosed? Q enclosed is the charge contained in the region contained in the Gaussian surface, which will be equal to lambda times L. The length of the cylinder is L, therefore the charge within that cylinder will be equal to lambda times L divided by epsilon naught. And what is this flux? Flux we have just calculated, E times 2 pi R times L is equals to lambda L divided by epsilon naught. Therefore, the expression will for the electric field will come out to be lambda times lambda by 2 pi R epsilon naught R cap. This is the expression for the electric field for a uniformly charged long straight wire. Okay, let's move to the next slide. We will see more examples where Gauss law is applied to calculate electric field in another video. That's all for this video. Thank you for watching. Please like the video and subscribe to the channel. Take care.